All right, so we're very happy to have Isabel Beach here from Toronto, and she'll tell us about the quantitative geometry of geodesics.
Great, okay, thank you for inviting me to this lovely trimester program. It's a pleasure to be here, as always. Right, so my name is Isabel Beach. I'm a PhD student from the University of Toronto. My advisor, Regina Rotman, is in the audience as well. Yeah, and as Fedja said, I want to talk to you today about the quantitative geometry of geodesics. So, first thing we want to know is what do we mean by quantitative geometry? So, essentially, this is an attempt to answer the question, if you give me an algebraic existence theorem for some geometric object, can I make a quantitative version of that theorem? So if that's a little vague, we'll see lots of specific examples today, specifically regarding where the geometric objects in questions are geodesics. So we're going to have several examples of some existence theorem. So there exists a geodesic with some properties, and then we're going to find out a quantitative version, which is there exists a geodesic with some properties, and it has length bounded in terms of the geometric properties of the underlying structure. We're going to be talking about several different kinds of geodesics as well. So I'm sure you all are aware of this, but if in case you're not, a geodesic is a curve that satisfies the geodesic equation. And of course, these are curves that have lots of interesting properties, as we'll see today. The first thing we're going to look at in particular are what are called closed geodesics. These are geodesic segments whose endpoints meet smoothly. So it's a closed curve, and you can parameterize it as a periodic function. So you can just keep going around and it's still a geodesic. So of course the classic example is going to be a great circle on a round sphere. So one of the first existence theorems that we're going to talk about today is due to Birkhoff, who proved that every Riemannian two-sphere has at least one closed geodesic. So this is our algebraic existence theorem, and a quantitative version asks how long can that geodesic be. So if we're requiring, these theorems are all relating it to the area of the sphere. So the statements are every Riemannian two-sphere area A contains at least one closed geodesic of length at most L. The first bound was proven by Croak in '88. He proved that you can bound it by 31 root A. And this was improved by Serre, Rotman, and Navitowski to 8 root A, and finally to 4 root 2 root A. So these are kind of some examples of quantitative theorems. For things that are not two spheres, an example of an existence theorem is Batlu-Starnik, who proved that any compact Riemannian manifold of any dimension admits a closed geodesic. In particular, this is true of all compact surfaces. And then there's this question of Gromov, which asks, is there a bound for the length of a shortest closed geodesic on a manifold in terms of the nth root of its volume? So if you're considering a non-contractible geodesic on a compact surface, this is sort of the purview of what's called systolic geometry. So many people have proved very beautiful theorems in this field. So I'll just name some names here. We've got Pugh, Loevner, Gromov, Hebda, Barago, and Zellgaller. And many others. Of course, this is only when it's not a sphere, but we just saw the sphere case earlier. Now, of course, this is for compact Riemannian manifolds. The next thing that's natural to ask is what happens if you have a complete manifold that is not compact. So this is a little trickier to prove the existence of a closed geodesic, because you can imagine, things are sliding off to infinity because there's no topology to obstruct them. In the case of a cylinder or plane. So here our existence results are due to Thorbergson and Bangert. So we've got here by Thorbergson that any complete Riemannian surface M with finite area that is not homomorphic to the plane or the cylinder admits a closed geodesic. In fact, infinitely many. And then Bangert proved the remaining cases of the cylinder and the plane, and I believe also the Mobius band. So in particular, any Riemannian surface with finite area admits a closed geodesic. So these are, again, algebraic existence theorems, and we're interested now in proving quantitative versions of these. So now that we know a closed geodesic exists, we want to know if we can bound its length in terms of the geometric properties of the manifold. So again, we have this paper due to Croak, in the same one where he proved his bound for the sphere. He proved that any complete Riemannian surface with finite area has a closed geodesic of length at most 31 root A. And so in my first paper, with my advisor in 2020. We just kind of improved this bound a little bit, in particular for the most difficult cases. This is the case of the plane and the sphere the plane and the cylinder, because these don't have any topological obstructions to control what happens with closed geodesics. So here we improved Crookes bound to 4√2 I'm not actually going to talk about that result today, but this is just kind of an overview at the start here. I think that's all I want to say about, another classic theorem about existence of closed geodesics, of course, is Lusternik-Schnirelmann, who proved that every two-sphere contains at least 3 simple closed geodesics. So now once we've got existence settled, it's interesting to ask, can there be more than one? And indeed, there's also an effective version of this theorem due to Lukimovich, Novotovsky, and Rotman, where they proved that, in fact, you can bound the length of these Lusternik-Schnirelmann geodesics by 5, 10, and 20 times the diameter of the underlying manifold. And I think that is all I want to say about closed geodesics, just to set the stage. Another natural object to consider is, probably this should have been technically the first example, because this is strictly a larger class than the closed geodesics. These are what are called geodesic loops. So these are geodesic segments that meet at their endpoints, but not necessarily smoothly. So technically, a closed geodesic is also a geodesic loop, but a geodesic loop is not a closed geodesic. So now I can have this angle here that is not equal to pi. There's no shortage of these in existence. I mean, here's an example of one on a hyperboloid. And these are kind of a special case as well of just a plain old geodesic segment. So if you want to consider all the geodesic segments connecting 2 points P and Q on your manifold, geodesic loops are the special case when P is equal to Q. So one of the big existence theorems for geodesic segments and loops is due to Serre in 1951, who proved that on a closed Riemannian manifold, there's actually infinitely many geodesic segments connecting any 2 pairs of points. And in particular, if your 2 points are the same point, you get infinitely many loops. And there's been some work on proving quantitative versions of this. So the first due to Novotovsky and Rotman in 2002, they proved that on a closed Riemannian surface between any 2 points, there are k geodesics of length at most 22k times the diameter, or 20k times the diameter in the case of a loop. So this is for any k, so you can imagine here what we're really saying is that there's infinitely many, and their lengths grow linearly as a function of the diameter. So the shortest has length 22 times the diameter, and the second shortest has like 44 diameter, and the third one has 6 times diameter, so this is really for all k. And then Hangi, who's also in the audience, I think. Yes, sorry, I couldn't see you. Improved this bound recently to 8 times the diameter, 8 times k times the diameter, or 6 times k times the diameter in the case of loops. And I think you also have a slightly tighter bound depending on like even and odd or some such thing. But yeah, so these are both quantitative versions of Serre's theorem. So if you're worried in particular about loops, somehow this is a slightly, this result is maybe not as general as you like, because you can imagine that if you have a closed geodesic passing through your point P equals Q, your k geodesic loops might just be the same closed geodesic iterated k times. So really the images of all your loops are the same. It's just whether you're going around once or twice or 3 times. So somehow it doesn't really make sense to say that there's infinitely many distinct loops. One way you can get around this is to look at if there's any simple loops, because 2 simple loops with different lengths are not going to be the same loop. And I proved a result to that end. That given any point in a Riemannian 2-sphere, there are 2 distinct simple geodesic loops based at that point, with length at most 7 and 14 times the diameter. So this result is very similar in style to the Lusternik-Schnirelmann theorem. So instead of having 3 simple geodesics on a sphere, it's 2 simple on a disk. Again, this is not the result I want to talk to you about today, but it's an example of the kinds of things that I prove in my work. So now we're going to go to kind of the main focus of this talk, which is a third type of geodesic called orthogonal geodesic chords. Yes.
Just to how does this relate to the quantitative Luther-Schnirelmann? So the quantitative Luther-Schnirelmann can give you 3 properties, right? And you say 2 closed loops. So why that theorem doesn't imply your? What's the difference? Just understand.
So they're doing closed geodesics, so there's no base point. So when they're shortening curves to get a geodesic, you can kind of flow all over. I have no idea where those curves are based.
I see.
Whereas this is about geodesic loops based at a point. So this holds it at every point. At every point on the sphere. Exactly. We're fixing a point. But it's otherwise very similar. Right. So orthogonal geodesic chords. So now this is on a manifold boundary, at least for the next 20 minutes. So this is a geodesic segment that starts and ends on the boundary of my manifold, and it meets the boundary orthogonally. An example is this half great circle and half round sphere. I guess these are called chords because historically, as we'll see, usually you're talking about a disk. So they're chords of a disk. So besides their intrinsic interest as geometric objects, these also have a relationship to, I guess you'd say, physics, the study of Hamiltonian systems. So if you've got this kind of standard form of a Hamiltonian system that you're interested in finding its solutions, where A is some, kind of like a matrix that's varying depending on where you are, and B is some function. If you use A as your metric, the solutions of this Hamiltonian system are equivalent to solutions of this equation, which you might notice is very similar to the geodesic equation with some potential V occurring, which might lead you to think correctly that these are going to be related to geodesics. So it turns out that each solution of these Hamiltonian systems has an energy that is constant for that solution. So each solution is going to lie in some sublevel set of the function B, which I can state this. So there's a special class of solutions to this system that are known as break orbits. These are essentially what I've drawn here. You can imagine a pendulum swinging. So these are periodic solutions to my Hamiltonian system, where the speed, so where P is 0 at time 0 and time equals t for some time t. And then as a result of having energy E, you're going to have the velocity, or Q, is going to lie on the level set of E at time 0 and t. So what you can imagine is V maybe is my gravitational potential energy. I'm starting with 0 velocity and I release my pendulum and it swings down and it comes back up, and then it gets to the top and has 0 velocity because it's changing direction. And it's just periodic between these 2 boundary points for all time. I will quickly note that this was a typo. These are not necessarily orthogonal. So the question is, how are these solutions of Hamiltonian systems related to our orthogonal geodesic chords? So it turns out that for a small delta, if you look at a slightly smaller sublevel set of my function V, so from minus infinity to E minus delta for a small delta, you can consider what's called the Jacobi metric, and it turns out that the orthogonal geodesic chords on this space with the Jacobi metric are uniquely extendable to these break orbit solutions on the entire of energy E. So so the study of break orbits is kind of equivalent to the study of orthogonal geodesic chords. And then I'll point out that there's interest in telling when these break orbits exist and if there are n of them. So Seifert proved that if your sublevel set is a n-dimensional disk, there's going to be at least 1 break orbit. And then he conjectured that there are at least n distinct break orbits of energy E. And Jambeau, Giannoni, Paccione proved, in fact, that Seifert's conjecture does indeed hold, using an argument about counting orthogonal geodesic chords. So that's just a little bit of motivation. We're going to not worry about the break orbits motivation, but we're just going to talk about chords. In the interest of proving cyclic conjecture, I believe Boss proved an existence result that a convex n-disk admits at least n orthogonal geodesic chords. So now we have this condition convex on the boundary, essentially 2 points that are nearby on the boundary, sufficiently close to be connected by a unique minimizing geodesic that lies within the disk. The reason this is helpful is that if you want to use curve shortening flow to find these geodesics, if your boundary is convex, your flow is going to be well behaved because things aren't going to be flowing trying to flow outside. So this is for disks, and then in 84, Gluck and Ziller proved that any manifold with convex boundary admits at least one orthogonal geodesic chord. So now we're interested in investigating how long these can be. Oh. And again, in analogy with the Lusternik-Straumann proof, we've got that Scott and Hasp, and then later Coe, using a different method, proved that for a two-dimensional disk with convex boundary, you get two simple orthogonal geodesic chords. And this is the first result I want to talk about today. So this is an effective version of this result. So a two-disk with convex boundary has two simple orthogonal geodesic chords whose lengths are bounded in terms of the perimeter and diameter. So perimeter plus 4 times the diameter. And then the second one is bounded by this slightly uglier linear function of the perimeter, diameter, and square root of the area. So not only are there two simple chords, they also have to have bounded length in terms of the geometric properties of the ambient disk. So again, this is kind of similar in flavor to the Lusternik-Straumann theorem proof. So what we're going to do is consider a Riemannian two-disk. We're going to consider a space omega m, where the critical points of the length functional on the space are going to be the objects that I'm interested in, so simple orthogonal geodesic chords. So I'm going to set omega m to be the set of piecewise differentiable paths in M with endpoints on the boundary that do not have transverse self-intersections. I'm going to look at these paths modulo the constant paths on the boundary. Yes?
But you allow some other type of intersections?
Yes, so they're allowed to be self-tangent. So this is okay because geodesics are not going to be self-tangent, so allowing them to have tangent self-intersections does not, that still means that the final geodesics are going to be simple. I mean, I think you could probably alter this to just say no self-intersections, but we'll see in the construction it's a little easier to allow yourself to double back along a path. So the first thing you have to do is define a length shortening flow in this space. And then you want to find some non-trivial homology classes in the space of paths modulo constant paths that are related by the cat product. So it's going to turn out for us that we're going to have two non-trivial classes, so we're only going to get two chords. And the fact that they're related by this product means that you can apply the Lusternik-Straumann type argument to prove that if the geodesics you get from each class coincide, you get an entire level set of geodesics with the same energy, with the same length. So this is going to allow us to ensure that our chords are distinct. Once you have these classes, you want to find a map that represents them that passes only through reasonably short curves. So they should have length at most Li. This length is going to be the bound for the length of your orthogonal geodesic chords because since you're applying curve shortening flow, you're never going to increase the length past your initial lengths. And then once you've got that, you want to apply the length shortening flow to the curves in the image of each representative. Then a subsequence of the longest curves in those images are going to converge to a simple orthogonal geodesic chord with length no longer than the initial length. And then as I previously mentioned, you get two chords, one for each class. If they end up being exactly the same, then you can use a standard argument to prove that there's actually infinitely many with that length. So in particular, there are at least two. So the first thing we have to do, which I did not do, I'm borrowing a procedure due to Haas and Scott. The details of your length shortening flow are not so much important, but I think this one is quite easy to state for the purposes of a talk. So if you're given a curve omega gamma in the space omega m of paths, you're going to be able to shorten it in the following way. So first, I'll have a picture of this at the end. So first you want to cover M by some small metric balls, so finitely many. By small, I just mean they should be, I believe, you could call this totally normal. So they should be convex, and I should be able to find a unique minimizing geodesic connecting any 2 points within them. So that's completely reasonable to ask. And then you look at the first ball, and you look at its intersection with my curve, and any segments of that intersection get replaced by a minimizing geodesic with the same endpoints. And then you look at any segments of that intersection that meet the boundary, and you replace those with geodesics connecting that endpoint to the nearest point on the boundary. And I'll show a picture of that, which I think explains it more clearly. So this is just done on the first ball, and then you go on to the second ball, third ball, up until you've exhausted all the balls. And then you repeat the entire thing ad infinitum. And eventually you should be getting a subsequence converging.
Is there not a problem? So if you want to, so you have to ensure that you stay, so that you don't get self-intersections.
Yeah, so it's actually interesting if you start with a curve without transverse self-intersections, you're not going to get transverse self-intersections in this method because essentially you're replacing things by minimizing geodesics in a ball. So minimizing geodesics are not going to, they can't cross each other. If the endpoints, if the initial curves don't cross each other, then the minimizing geodesics connecting their endpoints also can't cross transversely. It's essentially because minimizing geodesics can't form digons, like they can't, you can't have this kind of, I can't really draw it, but you can't have like a minimizing geodesic and then one that goes like this, because that would contradict minimality. I guess we have a little blackboard. I just realized that. Right, like minimizing geodesics cannot have this kind of thing, so as long as my initial curves did not cross, the minimizing geodesics connecting their endpoints also will not cross. So this is kind of the nice part about the Hausdorff process is that it's clear that curves are made simple, or maybe it's not clear, but it can be shown. So maybe here's a picture. So I've got 3 disks covering my curve. I look at the first disk, I replace that with a minimizing geodesic connecting this point to the boundary. And then I look at this middle disk and I replace the squiggly line with the straight line. And then I look at this disk and I replace the squiggly line with the geodesic. That's orthogonal to the boundary. So in this example, even after only one procedure, we're getting pretty close to an orthogonal geodesic chord. But this is essentially all that we're doing. So this curve has this flow has some properties that are especially useful for this. So again, it does not create transverse self-intersections, so it's a genuine flow on omega m. The curves are going to converge to simple orthogonal geodesic chords, or perhaps point curves. And when you apply this flow to a k-parameter family, the new family is homotopic to the original one. So that means when we apply it to our representatives of our certain homology class, we're not going to be getting out of that class. So the second thing we have to do is figure out what homology classes we want to use. This is more or less the same classes that you would use for the sphere. So the first one is going to be, so it turns out there's 2 classes. The first class in the Euclidean disk is represented by the settable chords parallel to the equator. I guess I did not draw the equator, but it doesn't really matter which day. So all of these chords make this one parameter family. And then the second dimensional class is just the settable chords. Now, of course, the question is, what does this mean on my manifold? Because I don't really know what a straight line, well, I know what a geodesic, I know straight lines kind of look like a geodesic, but there's not the same obvious choice. So instead what we're going to do is think about these chords instead of as pairs of radii. So I just map a chord to the pair of radii connecting its endpoints. So you can imagine the first class, instead of being the set of all chords parallel to the equator, it's these sets of pairs of radial lines that are it's symmetric across the y-axis. And the second class is just the parabol radii. So what we're going to do is we're going to find an analog of radial curves in my manifold, and then I'm just going to take pairs of those, and those are going to form my two homology classes that we're going to use. So what are we going to do that? First, we have to pick a point that's going to be the center that all of our radii are connecting to. So in order to utilize Bourget's lemma, I'm going to pick a point that's at maximal distance from the boundary. So this is my point P. And then Bourget's lemma tells me I can find geodesics emanating from P, such that the angle between any two neighboring ones is at most pi. So these geodesics are minimizing, so we know that they have length at most the diameter of the manifold. And we also know that this angle is at most pi, so these three regions are in fact convex. So this is going to be helpful for us because it means that when we apply the curve shortening flow, the flow is going to stay in each region. So what we're going to try to do is shorten each pair of geodesics, and then that's going to, in some sense, create a sweep out covering our manifold, and we're going to use that to create our radial curves. So I say try to shorten, because it's possible that we get stuck on an orthogonal geodesic chord. But assuming we don't, we can combine all these homotopies to sweep out the disk. And then we can just connect them to the center point to make our radial curves. Right, so if we do get stuck, the orthogonal geodesic chord we obtain is going to be no longer than the initial pair of geodesics, so it's going to have length at most twice the diameter. So this is actually good for us because that's quite short. We would not in general expect to be able to find a chord this short on every disk. But it's also problematic because we're looking for two. So to ensure that there's a second one somewhere, I really have nothing to do except to just try to shorten this further using some other alternative method. Because there's no guarantee that any of these other disks are going to get stuck on a chord. These disks might shorten, and then I've just got this one orthogonal chord, and then I don't have a second. So I really have nothing else to do but try to shorten this final disk. So there's a couple things you can do to get some intermediate bounds, but ultimately what you have to do, at least what I did, I should say, is use this very convenient theorem by Lukumovich, Novotovsky, and Rotman, which tells us how we can shorten the boundary of any disk in terms of its geometric properties. So the boundary of any disk can be contracted through a homotopy of loops based on its boundary, of length at most twice the perimeter plus twice the diameter plus 686 times the square root of its area. So this is why our bound for the second longest geodesic is quite nasty. It comes from this theorem. Unfortunately, there's not really much to be done about this constant. Obviously, unsurprisingly, it's quite difficult in general to shorten the boundary of any disk. Now, we did want to do curves that do not intersect because we're looking for simple chords and we want to make sure we're relying on omega n. But it turns out we can, by increasing the lengths a little bit in this theorem, we can make this happen. And this picture here is just kind of meant to be a schematic illustration of how this theorem works. Basically, you end up dividing your disk into subdisks and doing a kind of inductive process. You're trying to sweep up the little disks, and then eventually you can combine that to sweep out your total disk. But anyway, once we've done all that, we've figured out how to shorten all of our regions. So through some length L, so we've got our sweep out, then we can connect everything to the middle, and then we take pairs of curves to make our representatives of our homology classes. So in total, our length is going to be twice little l, which is however long it took us to sweep out these disks, plus the boundary, plus the diameter, which is the length of this geodesic. In fact, for the one-dimensional class, we can prove this a little bit, but this is essentially as good as we can do. So now we just have to use these sweep-outs to get an actual geodesic chord. So the way we do this is often called pulling type. So you want to apply the free boundary flow to the curves in the image of these representatives. So maybe I should first talk about the picture. So this is my path space. I've got the constant curves on the boundary line at the bottom. You can imagine the y-axis here is the length of your curve. So the curves of length 0 are my constant boundary curves. And I've got this non-trivial curve here, which is my one parameter family of curves. If I'm shortening it using the curve shortening flow, that's like pushing this down. So decreasing the length of everything in this family. But I can't push it down because it's stuck on this genus. And we know by Morse theory that it's stuck on this genus because there's a critical point here. So the critical point is this little black disk, and it corresponds exactly to a simple orthogonal geodesic chord. And that is how you get your chords of bounded length. And then, of course, after this, you have to do an argument about, well, what if my two classes gave the same chord? And you have to do a little homological argument there to ensure that you get a level set of distinct chords of the same length, but we're not going to discuss that today. So that was the first result. If there's any questions right now, of course, you can ask at the end. But after this, now I want to talk about an upcoming paper of ours that is kind of a generalization of this simple 2D disk case. So this has got a bit of a longer statement, but it also applies in much more generality. So this is due to myself. I did Contreras-Perriero, Aaron Griffin, Megan Kerr, Regina Rotman, and Catherine Searle. I probably should have said 2025 because this is not yet on archive. This is an upcoming paper still. Hopefully it will be out very soon. So this applies. Okay. I did not write this in full generality. In general, it'll apply to any pair of complete manifold n, m, and closed submanifold n, such that pi I of m relative to n is non-zero for some I. But I'm going to just talk about the compact case because then you don't have to worry about whether these classes exist. So what we're going to talk about today, we've got a pair of compact manifold and a compact closed submanifold. And then we've got some complicated condition involving shortening loops. So essentially what we need is that if we have a very long loop in my manifold that is based at a point on my submanifold, I should be able to shorten it by a moderate amount, so at least maybe shorten it by the diameter, through curves of bounded length. So this might sound a little bit specific, but it actually can be done in many cases. So for example, if you don't have short closed geodesics in your manifold, then you can always shorten closed curves because there's no obstructions when you apply the curve shortening flow, for instance. So the technical thing, maybe I'll just say it out loud. So we assume there are parameters A, at least as big as the diameter, and some other parameter C and some integer K, such that every loop in M that is based at a point on my submanifold, so every such loop of length at most 2ka plus delta for some small delta can be homotope to a smaller loop, which has length at most 2k minus 1 delta, and that homotopy passes through curves of length at most c. If this is satisfied, then there exists a geodesic chord in M that is orthogonal to n at its endpoints, and has length at most 2c times 2n plus 1. So the length depends on the dimension and the length of my shortening homotopy for all my loops. One critical difference I want to point out about this theorem versus the previous one, you are allowed in this theorem to take n to be the boundary of a manifold with boundary, but we are not requiring that the chord is not tangent to the boundary internally. So typically in the previous context, when we say orthogonal geodesic chord on a manifold with boundary, you're not allowed to intersect the interior, or the geodesic cannot intersect the boundary except at its endpoints. In this theorem, we are allowing that to happen. So if you don't want this to happen, you should also require that your boundary is convex, then you won't have this issue. But in general, if you're just thinking about submanifold, my geodesic chord can pass through the submanifold and intersect it in any weird way in the middle. We're just saying that at the endpoints, it is orthogonal. So it's a little more complicated than the previous example. But the strategy is quite similar. So now we've got a space. Now the critical points, or the orthogonal geodesic, the chords orthogonal to n are going to be the critical points of the space of piecewise differentiable curves in M that have endpoints on n. And we're going to do this quite similar thing. We're going to get a representative. Now it's going to be a representative of a homotopy class, so it's a map from the sphere into my loops into my path space. And I want to find a homotopic map that only passes through curves of length at most L. If we can do that, and my homotopy class is non-trivial, then we can apply the same pulling tight strategy to ensure that there's a critical point of length at most L. So in particular, a geodesic chord orthogonal to my submanifold. So much as before, all the work is kind of done in, if you give me a map, I have to make it shorter. So finding a short representative of whatever non-trivial class I have. So now our strategy is we're going to have first a little lemma that tells us how to connect. If you give me a path, I tell you how to connect the base point to every point on that path by short curves. So obviously you can just do this by following gamma itself, but then that's not necessarily short. We'll see pictures of this when we talk about this lemma. Then you want to find a non-trivial homotopy class that you want to make into, find a representative for that is passes only through small curves. So the first thing we do to make this representative that passes through small curves is we chop the domain into small rectangles. And then on each rectangle, we homotope F to a map that passes only through short curves using our lemma from step 1. And then we can glue these maps on these little rectangles back into a map from the original sphere to get a map that passes only through short curves. And then we can glue together the homotopies on each tiny rectangle to obtain a homotopy from map to G. So that's a lot of words to say that we're just trying to find a representative of our class that only passes through short curves. And we're going to use this lemma to do so. So basically what we want to do for our lemma is if we have a path eta, so it's got endpoints in this picture, I guess, on the submanifold. I want to be able to connect any point on this path to its base point by some short curve, which I call beta t. So in this picture, beta is not really all that shorter than eta, but you can imagine eta is really, really squiggly. So we want to show that there's a continuous family of curves beta t that connects eta 0 to eta of t, and the lengths of the beta t should be at most 2c, and if eta is a loop, the length of beta 1 should be small as well. So the way we do this is where we use our hypothesis that loops can be shortened in my manifold. So first I look at the arc of eta of length 2k minus 1a plus d. I connect my base point to that point by a minimizing geodesic. So this has length at most the diameter of the manifold and hence length at most a. So this whole thing is a loop based on n that has length at most 2ka plus delta. So that's why we had that strange hypothesis, because I want to be able to shorten this to a smaller curve, which we can do by hypothesis. So I end up with this smaller loop that has length at most 2k minus 1a. And then using that, we can make these short curves that connect eta naught to eta t. So I start at eta naught. At first, I follow eta itself until I get to that point, and then I extend out a bit to get my geodesic and my loop. And now that I've got my loop, I contract my loop, and I end up with this relatively short curve that connects eta 0 to eta 2k minus a plus delta, or whatever it was. And then to proceed, so that gets us beta t for t in here. To finish off, we start connecting, we go on a small delta along here, and then connect this point by another minimizing geodesic. Then we got a new loop that is short, and then we contract that loop, and we keep on proceeding in this manner. So that's how we do our little lemma that we're going to use later. The next thing we have to do is find a non-trivial homotopy class, relative homotopy class. So it turns out, just by considering the parameter of your paths, that the homotopy group of omega and m mod n is isomorphic to the I plus first homotopy group of m comma n. So to do this, essentially, you just remember that a point in this space is a path in this space, so you get an extra parameter, one-dimensional parameter. So in general, there does not have to be a non-trivial homotopy class here. If n is a circle inside of a cylinder, there's not going to be any geodesics orthogonal to n that meet n at 2 points. If I want to leave here orthogonally, I'm just going to keep going forever on a straight line. I'm not going to come back. So this case doesn't, you can't always prove this, you do this theorem, but if m and n are both closed, then you're always going to end up having a non-trivial homotopy class. So in that case, it is okay. And in the pictures that follow, I'm going to assume that the fundamental group is non-trivial, so I'm just going to draw everything in one dimension. So I'm going to have some one-dimensional non-trivial homotopy class represented by f. This is a map of S1 into my path space. So I've got S1 here, mapping into some non-trivial closed curve. And I'm going to divide S1 into little intervals of like 2 epsilon. So this blue interval gets mapped to this little segment of my curve. And then I can remember that this curve is a rectangle in my manifold, where the 2 edges of the rectangle lie in the manifold N. And when I say I want my rectangles to be tiny, I'm just meaning that these kind of cross-sectional lines should be small, which we'll see in a second here. So now we want to construct my map GR that passes only through small curves and is homotopic to F. So we're going to be able to do this through curves of length at most 6c. So to start, we define it on minus epsilon and epsilon, so just the endpoints of my interval. What we do is we connect this point to every point on this vertical edge using our lemma. That tells us we can connect paths, any point on a path, to the base point by short curves. And then we take that final curve that connects to the 2 endpoints of fr minus epsilon to get gr minus epsilon. And then we do the same thing on the other side to define it on epsilon. So to define it in the middle, we just need to homotope between these 2 curves on the end. And we're going to do so by contracting this big loop. So the bottom horizontal line followed by gr minus epsilon, followed by the top horizontal line, followed by gr epsilon. If you can contract this loop, then you just do this loop followed by gr minus epsilon, and that's going to give you a homotopy between this guy and this guy. So we do so using the curves from our lemma, and also using these horizontal guys. So I picked epsilon so that all of these horizontal curves have some bounded length at most delta, where I pick delta as small as I want. So we contract the loop essentially by going down a little bit. So remembering the curves from my lemma that connect to f epsilon at time equals, say, 1 minus epsilon. Then I cut across. And then I go down the other side, and then I just kind of push everything, keep pushing everything down until I end up at the bottom on n. And all these homotopies are relative to n, so once I'm in n, I'm good to go. So this defines all the curves in GR. So a generic one looks just like some loop in that homotopy, followed by gr minus epsilon. And of course, FR is just some vertical curve in my rectangle here. So this guy has length at most some small delta, plus 2c, plus small delta, plus 2c, plus small delta, plus 2c, plus small delta, so it's going to have length at most 6c. If we want to homotope, now we want to homotope between f and g. We actually do this in a very similar way to how we define g itself. So we start with f, modulo some stuff in n, and then we start adding a little bit of our loop here, then following up to height t, then following the rest of f. And then I keep going, pushing up in this way, until eventually I reach t equals 1, and then I've just got only g is left. So At time equals 0, I have f. At time equals 1, I have g. And now I've got a homotopy between them. The parameter x here is controlling kind of like which loop I have here, but the height is the parameter of the homotopy itself. So it's going to turn out that these are all the same on the boundaries of the rectangles, so we can glue them all together. It's a homotope from F to G. So this finishes the construction of G. But then the question you want to know is, where can we actually apply this theorem? So I want to see some examples here. So obviously you can do this, you can apply this theorem to any manifold where you know that you can shorten all the curves. That's not so hard. That's kind of just what the theorem says. But it turns out that actually you can also apply it even if you only know how to shorten curves in the submanifold. So you can imagine maybe you have some submanifold, you know how to shorten all the curves on really easily, and it's embedded in some larger space you don't know anything about, and you want to know, are there orthogonal geodesic chords to that submanifold? So it turns out that actually you can do that. So what you need to do, so assume you can shorten curves in your submanifold with that same hypothesis we had before, and also assume that there are no stable geodesic chords orthogonal to n of short length. If this is true, then you can prove that there is a chord in M orthogonal to n that has length at most 12c times 2n plus 1. So 6 times as long as if you knew how to shorten all the curves in M, but still not bad. And of course, this second condition that there's no stable orthogonal geodesic chords is actually not an obstruction because that's what you were trying to find. So if you knew you had a short one, you'd be even happier. So really, as long as you can shorten loops in n, you can get a geodesic chord orthogonal to n. So I'll just quickly go over how you can do that before showing you a nice concrete example. So you want to figure out how to shorten curves, how to shorten a loop that lies in my ambient space that is based on n, because this is the hypothesis of our theorem. So I've got this loop alpha. And what I can do is apply the free boundary curve shortening flow to alpha in M. So I just think of it as a segment with endpoints on my submanifold, and I do the length shortening flow while fixing that the endpoints have to remain on that submanifold. So the critical points here are going to be orthogonal geodesic chords, orthogonal to n. So if I assume that there's none that are shorter than alpha, I'm going to be able to contract alpha to a point using this method. So I've got this nice homotopy here. Then I can look at the, what do I call this? The trajectories of the endpoints on n. So now this is a loop in my submanifold. So by hypothesis, I know how to shorten this because that was what I said. But we also know that we can apply our lemma now from before, where we can connect every point on a curve to the base point through short curves. So now I can do that in n. So I've got all these curves connecting points on my trajectories to the base point. And I'm going to use this fact to homotope my original loop alpha to this final loop beta 1. I'm going to point out that I don't know that, even though this is a closed loop, I don't know that beta 1 is a point curve necessarily. And the way we do this is as follows. Got my loop alpha. I kind of go out along beta 1 minus beta 1, so this is still homotopic to alpha. And then I start kind of looking at I start flowing alpha and connecting it to the base point using the curves from my lemma. Then I've also got this beta 1 hanging around. So one of the beta 1s is turning into this curve, and the other one's getting left behind. And the second curve is coming from the fact that beta 0 is a point curve, so that's okay. Then I keep flowing alpha, keep connecting it to the base point by my curves from my lemma that are short, until finally I end up with beta 1 plus this curve followed twice, which of course then I can just contract this guy followed twice to get beta 1 back. So the longest curve in this family is going to be the length of beta 1, plus the length of these two black curves, plus the length of alpha. So it's going to have length almost 6c. This is where our length bound comes from, because now we've just got 6c in place of c, so 12 is 6 times 2. And finally, I'm going to finish off by a more concrete example of where this theorem actually applies. So now I've got a closed Riemannian manifold of dimension n and a submanifold that is a two-dimensional sphere. So again, using our theorem that we had before, we know that we can contract any disk through loops of short length bounded by this linear function of the perimeter, square root area, and diameter. So you can make a version of this where instead of a disk, I've got a loop on a sphere. And you can bound these quantities in terms of the quantities of the manifold n and m. So then you know how to shorten curves on my two-sphere. And then I use that theorem to prove now that there's got to be an orthogonal chord in M that's orthogonal to my two-sphere that has length at most. So now C is going to depend on this guy, so it's going to be very large. So it ends up being about 12 times C ends up being 4 diameter M plus 96 diameter M plus 8,232 times the square root area times 2 times the dimension of M plus 1. So my chord could be terribly long, but this applies for any ambient manifold containing my two-disk, or my two-sphere. So it's kind of interesting that this bound exists, at all. Of course, there's many other places you can apply this theorem, but this is just one that to show how you can do it. And then, of course, one of the dissatisfactory things about this theorem is that it proves the existence of one orthogonal chord. So a way that you could we can maybe continue this work would be to try to prove the existence of multiple. Obviously, that's not going to be true necessarily in general, but for instance, you could try to prove a quantitative version of Boss's theorem so that there's n distinct chords in an n-disk of bounded length. Another generalization that we're interested in is viewing orthogonal geodesic chords as kind of the one-dimensional version of free boundary minimal submanifolds. So those ones are sort of like instead of decreasing length, you're trying to decrease the volume. So kind of a higher dimensional analog to this theorem that would be of interest to me is to find to say that in a manifold boundary, you've got a free boundary minimal submanifold of bounded volume. Of course, again, this is not something you'd expect to be true in general, but I would be interested in proving a result to this end. And that is all I had prepared. Thank you very much for listening to me.